colour of a star seems like the simplest thing about it. You learned it young. Blue stars are hot, red stars are cool, and the light just tells you the temperature. But in 1917, an astronomer named Vesto Slipher pointed a telescope at 25 faint spiral smudges and measured their light. 21 of them were racing away from Earth, some at up to 1.1 million miles an hour. Nobody in the world could say why, and the whole clue was hidden in nothing but their colour. This is redshift. It is the quietest and strangest fact in all of astronomy. The starlight landing on your eyes right now has been stretched. Not dimmed, not bent, stretched. The wave itself is longer than it was when it left the star. And the thing doing the stretching is not the star. And it is not the empty gap it crossed in any ordinary sense. It is space itself, growing larger during the journey. That is the reveal that took a century to believe. When you look at a distant galaxy, you are not seeing it as it is. You are seeing light that left it long ago, and that light has been physically altered on the way. The universe you see is already gone. The colour is a fossil. If that idea keeps you awake in the good way, take a moment to subscribe to Deep Space Drift and follow the audio version on Spotify. It genuinely helps the channel grow. Then stay with me and we will decode what your sky's really saying. Start with sound, because your ears already know this trick. An ambulance races toward you, and its siren rides high and tight. It passes, and the pitch drops and stretches low. The siren never changed its note. The waves did. Moving toward you, they bunch up short and high. Moving away, they stretch out long and low. Light behaves the same way. Move a source of light away from you, and its waves stretch toward the red end of the spectrum. Astronomers call that a redshift, a falling pitch you can see instead of hear. Move it toward you instead, and the light bunches toward the blue. That is a blue shift, the colour equivalent of a rising siren. It sounds like a small effect. It is the master key to the entire universe. And the beauty of it is that you never have to travel to the star. You only have to read its light carefully. So how do you measure a shift without ever touching the source? You read its fingerprints. Every element leaves a signature in light. Hydrogen, helium, calcium, sodium, each one absorbs and glows at exact known wavelengths. In a laboratory here on Earth, hydrogen shines at colours we have measured to staggering precision. Those are its rest wavelengths, its true colours when nothing is moving. They never change. That is what makes them useful. When starlight comes in, those same fingerprint lines are there, but they have slid. The whole pattern has moved toward the red, every line shifted together by the same fraction. Because the pattern is so distinct, you can measure exactly how far it travelled. That shift has a number, and astronomers call it Z. The formula is almost insultingly simple. You take the observed wavelength, subtract the rest wavelength, and divide by the rest wavelength. That is Z. If Z equals 0, nothing has shifted, and the object sits at rest relative to you. If Z equals 1, the wavelength has doubled. The light left the source as one length, and arrived at your telescope twice as long, stretched to exactly double on the way here. Sit with that number for a moment. A Z of 1 means the light you catch is twice the size it was when it started. The universe grew while the light travelled, and the light grew right along with it. A Z of 2 means it has tripled. The higher the number, the more the sky has stretched. This is why the night sky is a kind of fossil record. Nearly every point of light beyond our own galaxy is already redder than it truly is. A permanent tint, stamped on by the expansion of space, invisible to your naked eye but written all over the spectrum. You cannot spot the shift just by looking up. You can only find it by reading the fingerprints, but it is there, on almost everything, all the time, whether anyone measures it or not. And here is the part that unsettles people the first time they truly understand it. The light reaching your eyes right now has been thinned by the fabric of space expanding underneath it during the flight. You're not just looking at old light, you're looking at light the universe physically changed while it was in transit. Every distant galaxy hands you a message that the messenger altered on the way. For most of human history, nobody suspected any of this. The sky was assumed to be fixed, eternal. The same stars your grandparents saw, the same ones a Roman farmer watched, the same ones that will burn unchanged forever. Then a patient man on a cold mountain in Arizona started photographing smudges. His name was Vesto Slipher. He worked at the Lowell Observatory in Flagstaff, high up where the winter air bites and the stars hold still and sharp. In 1912 he began aiming a 24-inch refracting telescope at what astronomers then called spiral nebulae. Faint, fuzzy pinwheels of light. Nobody knew what they were. Many believed they were clouds of gas inside our own Milky Way, small and nearby. They were not. Each one was an entire galaxy, millions of light years away, holding billions of stars of its own. But Slipher had no way to know that yet. He had only their light, a spectrograph to spread that light into its colours, and long freezing nights to gather enough of it to measure. The work was brutally slow. A single exposure could take all night, sometimes several nights stacked together, one photographic plate at a time. He would sit in the dark, guiding the telescope by hand, holding a faint galaxy steady on a sliver of glass for hours while the cold crept into everything. Then he would develop the plate and measure, by eye, where the fingerprint lines had landed. On September 17, 1912, he turned the telescope toward the Great Nebula in Andromeda. He gathered its light and read the lines, and the fingerprints had shifted the wrong way. They were blue-shifted. Andromeda was not fleeing at all. It was coming toward us at about 300 kilometers per second, roughly 671,000 miles an hour. That alone was a shock. Nothing in the heavens was supposed to move that fast. But Andromeda, it turned out, was the exception, not the rule, and that oddity would matter enormously later. Slipher kept working through the cold. By 1914 he had measured 15 of these nebulae. 12 of them were redshifted, their fingerprints sliding toward the red, their light stretched, moving away from us. Only a few approached. When he presented the results to a room of astronomers, they rose and gave him a standing ovation, even though nobody in that room, Slipher included, understood what the numbers meant. By 1917 the tally had grown to 25. 21 were racing away. Some receded at up to 1.1 million miles an hour, faster than anything anyone had ever clocked in the sky. The pattern was overwhelming and lopsided. Almost everything was fleeing, and only a rare handful drew closer. The sky was not fixed. The sky was in motion, and mostly in one direction, outward. And that is where the trouble began, because a sky in which almost everything is rushing away is a sky that cannot be standing still. Think about what that lopsided pattern demands. If nearly every galaxy is receding from us, then either we sit at the exact dead centre of some cosmic explosion, which seemed absurd, or something far stranger is true. The space between the galaxies is growing. Not the galaxies flying apart through space like debris, but space itself swelling in every direction at once, carrying everything along with it like markings on an inflating surface. Slipher had the numbers. He did not have the meaning. He had measured the expansion of the universe more than a decade before anyone owned the framework to explain it. The velocities were real, recorded on glass. The theory that could hold them did not exist yet. Even Albert Einstein pulled back from it. When he applied his new equations of gravity to the whole cosmos in 1917, the math refused to sit still. It wanted the universe to either expand or collapse. It would not stay static no matter how he arranged it. Einstein did not believe the universe could truly be doing either. So he added a term by hand, a fudge factor, to hold everything in balance. He called it the cosmological constant. It existed for one reason only, to keep the universe eternal and unchanging, because that is what every educated person knew to be true. He was patching his own equations to match a universe that was not there. The real universe, the one Slipher was catching on photographic plates on freezing Arizona nights, was already expanding. Einstein would later call that patch the biggest blunder of his life. The meaning arrived from a quiet direction. In 1927, a Belgian physicist named Georges Lemaitre, who was also a Catholic priest, worked back through Einstein's own equations and simply let them do what they wanted. He concluded that the universe is expanding, and he derived a relationship from it. The farther away a galaxy sits, the faster it should be receding. He even estimated the rate of it. Almost nobody read him. He published in an obscure Belgian journal in French, and the results sat in near silence for years. He held the law 2 full years before the man whose name it would carry. That man was Edwin Hubble. Working at the Great Telescope on Mount Wilson in California, Hubble did the one thing Slipher could not. He measured distances. He used a special kind of star called a Cepheid variable, a star that pulses at a rate locked precisely to its true brightness. Compare that true brightness to how faint the star looks from here, and you get its distance. Astronomers call such stars standard candles, because their glow is a known quantity. Hubble took Slipher's velocities and married them to his own distances. In 1929, he published the result. Precession speed is proportional to distance. Twice as far, twice as fast. It was the exact relationship Lemaitre had written down 2 years before. Today we call it the Hubble-Lemaitre law, at last giving both men their due, and with that, the static universe was dead. Not doubted, not merely weakened. Dead. The sky was not eternal and fixed. It was expanding, and it always had been, and the redshift in that starlight was the proof, stamped on nearly every galaxy at once, waiting all along for someone to read it. By the end of tonight you will understand what that expansion is doing to the sky above you, where it is carrying every galaxy, and why the universe may be quietly hiding its own history from anyone who looks up too late in the story. But first, we have to slow down and be careful, because the single word redshift is doing far more work than it looks. When Slipher saw Andromeda drifting toward us while the rest of the smudges fled, he was watching more than one process at the same time. A galaxy's light can redden because the galaxy truly moves away from you through space. It can redden because the space in between is swelling while the light is in flight. It can even redden because the light is climbing out of a pit of gravity so deep that time itself runs slow at the bottom of it. 3 different causes. 1 colour shift. In the light they look almost identical, and telling them apart is the whole game. Picture the man before the telescope alone. His name is Vesto Slipher, and the mountain under him is cold Arizona rock, dark and thin at the top of the air. The instrument he leans into is a 24-inch refractor at Lowell Observatory, a long glass eye pointed up at faint smudges nobody could yet explain. This is 1912. He's not looking for a moving universe. He's simply trying to photograph the colour of light from fuzzy patches in the sky, the ones astronomers of the day called spiral nebulae, and no one on Earth knows what they truly are. The work is slow in a way that is hard to imagine now. A single exposure can take all night. Light drips onto a photographic plate 1 thin trickle at a time, and Slipher sits inside the dome like a watcher inside a cold shell, waiting, adjusting, keeping the faint smear centered while the whole sky wheels overhead. When it is done, the plate goes into the dark to be developed, and the image rises out of the chemicals like a slow, silver memory forming where there had been nothing. He's reading starlight the way you might read a fingerprint, comparing where the known lines of hydrogen sit on his plate against where they sit in a laboratory at rest. On September 17th, 1912, he turns the glass toward the great nebula in Andromeda. He develops the plate, he measures the lines, and the fingerprints are shifted the wrong way, not stretched toward red, but squeezed toward blue. Andromeda, whatever it is not fleeing. It is coming toward us, and fast, at roughly 300 kilometers per second. Put that in plain numbers and it is about 671,000 miles per hour. It is the largest velocity anyone has ever measured for an object in the heavens, and it points straight at us. He keeps going. Night after night, plate after plate, he adds new smudges to his list, and here the pattern begins to turn strange. Andromeda came toward us, but the next one flees, and the one after that flees. By 1914 he has measured 15 of these nebulae, and 12 of them are shifted toward red, which means 12 of them are running away. He stands up in front of a room of astronomers that year and reports it, and the room does something rooms of scientists rarely do. They applaud. Still no one knows what they are looking at. To Slipher and everyone around him, these are nebulae, clouds, patches of glowing stuff somewhere inside our own star system, or just beyond its edge. Nobody in that room yet understands that each fuzzy patch is an entire other galaxy, a wheel of 100 billion suns so far away that its light has crossed a gulf the mind cannot hold. He is measuring the flight of whole galaxies and calling them clouds. He does not stop. By 1917, the list has grown to 25 nebulae, and 21 of them are redshifted, racing away. The fastest of them is pulling back from us at around 1,100 kilometers per second. That is roughly 2.46 million miles per hour, a speed with no earthly meaning, printed quietly onto glass plates in a cold dome on a mountain. One patient man, working mostly alone, has built the first real evidence that the universe is not still. He has the velocities. He simply does not have the second half of the puzzle, and he cannot get it, because he has no reliable way to know how far away any of these things are. That missing half is distance, and it arrives from other hands. Down in California, Edwin Hubble is working the giant telescope on Mount Wilson, and he finds a particular kind of star inside some of these nebulae. Cepheid variables, they are called, stars that pulse brighter and dimmer on a steady clock, and the speed of that pulse tells you how much light they truly pour out. Compare that true brightness to how faint they look from Earth, and the distance falls out of the arithmetic. These are the standard candles, and with them Hubble can finally measure the gulf that Slipher could not. Now watch what happens when the two halves meet. Take Slipher's velocities, the redshifts, the numbers pulled off those long cold exposures, set them beside the distances measured by the pulsing stars, line them up, and a simple, almost unbelievable rule appears. The farther away a galaxy sits, the faster it is running from us. Double the distance, and you roughly double the speed of retreat. The recession is proportional to the distance. Hubble publishes this in 1929, and it lands like a bell struck in a quiet church. The universe is not a fixed room, it is growing. But the story of who saw it first is not as tidy as the textbooks once made it. 2 years earlier, in 1927, a Belgian named Georges Lemaitre had already put it together. He was a physicist, and he was also a Catholic priest, a man comfortable holding equations in one hand and a faith in the other. Working from Einstein's own theory of gravity, Lemaitre derived the very same relationship, that galaxies should recede in proportion to their distance, and he even estimated the rate of that expansion. He had reasoned his way to an expanding universe before Hubble ever published the measurement of it. But Lemaitre wrote in French, in a small Belgian journal that few of the great observatories read, and his key result was quietly dropped from the English translation that circulated later. So the credit ran for the better part of a century to Hubble alone, and the rule became simply Hubble's law. Only in recent years did astronomers vote, formally, to set the record straighter. Today, you will find it in the newer books under both their names, the Hubble-Lemaitre Law, a priest and an observer sharing one sentence about the shape of everything. And there is a third figure standing in the shadows of this discovery resisting it, Albert Einstein. His own equations of gravity, written in 1950, quietly insisted that the universe could not sit still. They wanted it to either expand or collapse, never to hold. But Einstein, like nearly everyone of his age, believed deep down that the cosmos was eternal and unchanging, a fixed and finished thing. So he did something he would come to regret. He reached into his own beautiful equations and added a term by hand, a number invented for no reason except to hold the universe motionless. He called it the cosmological constant. It was a fudge, a small weight dropped onto the scales to keep them from tipping, and its only job was to keep the sky still. Then Slipher's redshifts and Hubble's distances arrived, and the sky was not still at all. It was flying apart in every direction. Einstein had bent his own theory to forbid the very thing the plates were now proving. The story goes that he came to call that invented constant the greatest blunder of his life, the moment he let his instinct for a quiet, permanent universe override what his mathematics had been trying to tell him all along. His equations had predicted an expanding cosmos, and he had refused to believe them. So sit for a moment with what one careful man on a cold mountain set in motion. Slipher never claimed to have found an expanding universe. He was cautious, quiet, a measurer rather than a theorist, and he handed the world a table of numbers without the grand conclusion attached. But those numbers were the seed. Every redshift he pried off a glass plate, every long night in the shell of that dome waiting for a silver ghost to rise out of the developing bath, was a single reading in the first survey of cosmic flight. 21 out of 25, all running, some at more than 2 million miles an hour, and one lone exception sliding toward us out of the dark. That is the strange gift these early astronomers left you. When you look up now and think of galaxies streaming away, you are really standing on the shoulders of a man photographing clouds he could not name, a priest writing in a language the world ignored, an observer counting pulsing stars, and a genius who had been dragged, against his own instinct, into a moving universe. They built the idea one careful measurement at a time, and the tool they built it from was the shift of light toward red. That shift became the yardstick for the entire cosmos, the single number astronomers trust to tell them how far, how fast, how long ago. And yet the deeper you follow it, the more you find that the yardstick has hidden layers. But not every redshift means the same thing, and not every one of them is a galaxy actually moving at all. But not every redshift means the same thing. Not every one of them is a galaxy actually moving at all. That is the strange twist hiding inside the word. A shift toward red looks like a single effect. It is really three effects, and they arrive by three completely different roads. Learn to tell them apart, and the sky starts to speak in a clearer voice. The first road is the one your body already understands, Doppler redshift. An object moving away from you through space, its light stretched by that motion, in the same way a passing siren drops in pitch as it goes by. A police radar gun reads this exact shift. A receding ambulance sings it. This is real motion, real speed. Something travelling through space, away from where you stand, its light reddened by the going. The second road is stranger, and it is the one that rewrote the universe. Cosmological redshift. Here nothing needs to be moving at all. The light leaves a distant galaxy, and while it is in transit, the space it crosses expands. The wave gets stretched because the road it rides on gets longer under it. The colour shift does not measure the galaxy's speed. It measures the swelling of space itself, recorded in the light like a watermark. Hold that difference in your mind, because it changes everything you thought you were seeing. Two galaxies can sit perfectly still, neither one paddling anywhere, and still drift apart. Picture two rowers on a wide river. The river itself is widening beneath their boats. Neither rower lifts an oar, yet the gap between them grows and grows. That is cosmological redshift. The water is doing the work, not the rowers. The distance opens on its own. So the recession you read in most galaxy light is not truly a speed. It only wears the costume of one. The void between here and there is inflating, the way the skin of a balloon swells when you breathe into it. Ink two dots on that balloon and blow. The dots rush apart, yet neither dot moves across the rubber. Every point retreats from every other point. No point is the centre. Call it a velocity if you like. It is really just the fabric growing while the light is still on its way. Then comes the third road, the quietest of the three, gravitational redshift. This one has nothing to do with motion, and nothing to do with expansion. It is about weight, about what gravity does to time. Light climbing out of a deep gravity well loses energy on the way up. Not speed, because light never changes its speed, but energy. And for light, lower energy means a longer wavelength, a slow slide toward the red. Think of a single photon as a swimmer at the bottom of a very deep pool, kicking hard to reach the surface far above. It gets there, but it arrives tired, spent, and redder for the long climb. Every heavy object in the universe taxes the light that tries to leave it. The reason underneath is deeper still. Time itself runs slower down inside a gravity well. A clock resting near a heavy mass ticks a little, behind a clock hanging far away in empty space. Light borne down in that slow region carries the slowness with it, and when it reaches you, you read that lag as a stretched colour. The redness is a message about time. The photon is telling you how slowly its birthplace ran. This is not a theory that only lives on a chalkboard. It was measured, here on Earth, in 1959. Two physicists named Pound and Rebka set gamma rays climbing a tower at Harvard, a tower only about 74 feet tall. That was all the height they had to work with. And in that short rise from the basement to the roof of a single building, the light reddened by exactly the sliver Einstein's equations had demanded. Gravity had bent time by a measurable hair inside an ordinary stairwell, and they caught it in the act. So now you hold three redshifts wearing the same red coat. One born from motion through space, one born from space itself expanding, one born from gravity draining a photon on its way out of a well. And here is the trouble. In the raw light, they look alike. A stretched line in a spectrum is a stretched line. Nothing about the colour by itself tells you which of the three roads it travelled. How could anyone ever pull them apart? Inside a single galaxy, sometimes you cannot. Not cleanly. But gather a whole cluster of galaxies, hundreds or thousands of them bound together in one gravitational knot, and a pattern rises out of the crowd. Doppler motion inside a cluster is random. Some galaxies swing toward you, some swing away, orbiting through the shared gravity. Their shifts scatter evenly to both sides of the average. Blue balances red. The spread widens, but the centre stays put. Gravitational redshift behaves differently. It does not scatter, it leans. Every galaxy sitting deep in the cluster's shared gravity has its light reddened in the same direction, all of it nudged the one way, because they are all climbing out of the same well. So astronomers watch the mean of the whole distribution rather than any single galaxy. Doppler motion only fattens the spread, symmetric and even, still centered where it was. Gravity slides that entire center gently toward the red. The scatter tells you about movement. The shift of the mean tells you about weight. Read one pile of starlight carefully enough, and it will confess both secrets at once. And now, the exception. The single bright object that breaks the universal rush, and in breaking it, proves the rule everywhere else. Almost everything in the deep sky is redshifted, fleeing, reddening, retreating into the distance. But turn your telescope toward Andromeda, our nearest large neighbour, and the light comes back the wrong colour, not stretched, compressed. The waves squeeze toward the blue end of the spectrum, the unmistakable signature of something drawing closer instead of pulling away. In a sky full of retreat, one great neighbour is coming home. Andromeda is falling toward us. It approaches at about 110 kilometres every second. In the units you actually live by, that is roughly 246,000 miles an hour, close to 68 miles every single second, an entire galaxy of 1 trillion stars sliding steadily down the sky in our direction. Vesto Slipher caught the first faint hint of this back in 1912, years before anyone even understood that Andromeda was a separate galaxy at all, and not just a smudge of gas inside our own. Why this one exception? Why does nearly everything else flee while Andromeda charges straight in? The answer is distance, and the quiet tug of war that distance sets up. Andromeda sits about 2.5 million light-years away. That sounds impossibly far, and by any human measure it is. But on the scale of the cosmos, it is next door, close enough that a different force still rules the space between us, close enough that gravity still wins here. The Milky Way, Andromeda, and dozens of smaller galaxies form a bound family called the Local Group. Inside that family, the combined pull of all that mass overpowers the gentle outward stretch of expanding space. Expansion is real everywhere, in every gap, in every inch. It is simply weak. Over short distances, ordinary gravity beats it without effort. The balloon is still inflating under the whole local group. It just cannot tear our neighbourhood apart because we are holding on to each other too tightly for the stretch to matter. That is the clean lesson Andromeda quietly teaches you. Cosmic expansion does not carry away the things that are gravitationally bound to you. Your galaxy will never stretch. Your local group will never stretch. The atoms in your hand will never drift apart from the pull of expanding space. Only out beyond the bound structures, in the enormous gulfs between galaxies that hold no grip on one another, does expansion finally take command and the redshift return. Andromeda's blue light marks that boundary line for you. It shows exactly where local gravity ends and the great rush begins. There is a strange beauty in imagining that approach across time. Andromeda grows a little nearer with every passing year, silent and vast. 4 or 5 billion years from now, on some far future night, it would swell across the sky, spreading wider than the full moon, an entire second galaxy of light rising over the horizon before a single star of ours had touched a single star of theirs. 2 spirals leaning toward one another across the dark, close enough at last to feel each other's weight. For most of the last century, that story ended in a certain collision. The textbooks drew it as a done deal. Andromeda would arrive, plunge headlong into the Milky Way, and the 2 great spirals would tangle and settle into a single giant elliptical galaxy. It was told as a fact of the future, as sure as tomorrow's sunrise. But the honest answer, the one the newest measurements actually give, is far less certain than that. Recent modelling, built on sharper velocity and mass data than the old story ever had, no longer calls the merger a sure thing. When you fold in the sideways pull of the other local group members and you carry the real error bars all the way through, the odds of a true merger within the next 4 to 5 billion years come out close to a coin flip. Something near even, either way. A near miss is now a genuine possibility. The 2 galaxies might swing past one another instead, tug and distort each other's arms, and then sail on apart for billions more years before anything finally settles. The old certainty has softened into a real maybe, held open by honest uncertainty rather than closed by wishful storytelling. It is a good reminder that even the nearest, best measured, most studied object in all our sky still keeps a piece of its own future hidden from us. So the 3 redshifts sort themselves out at last. Motion through space, space itself expanding, like climbing wearily out of gravity's wells, and one blue exception falling toward home to remind you that gravity still holds its own small kingdoms against the tide. Underneath all of it, one process keeps working in the dark, in every empty gap between the bound islands of matter. Space keeps stretching. That is the deep engine that reddens the sky. So how does anyone actually catch light in the act of stretching? You cannot see it with your eyes. A galaxy simply looks like a smudge. The trick lives in the light itself. Once you spread it out into its colours, every element leaves marks in light. Heat a cloud of hydrogen in a laboratory, and it glows at exact colours, never a smear. Those bright colours are emission lines. Let white light pass through a cooler gas instead, and the same element bites dark gaps out of the rainbow. Those are absorption lines. Either way, Hydrogen always prints the same pattern at the same places. Helium prints a different one. Calcium, sodium, iron, each has its own signature. Think of it as a barcode pressed into the light. Every element carries its own set of lines, spaced in a way nothing else copies. When you spread starlight into a spectrum, those lines show up as a run of stripes, thick and thin, exactly where the chemistry demands. It is a fingerprint the universe cannot forge. And here is the quiet magic of it. We know precisely where each stripe belongs, because we have measured it on Earth, in still air, in a jar of gas that is not going anywhere. That measured position is the rest wavelength. It is where the line sits when its source is sitting still beside you. So when astronomers photograph a distant galaxy's spectrum, they are not guessing. They already know the pattern by heart. They lay the observed stripes over the laboratory stripes and look for the offset. And in almost every galaxy, the whole barcode has slid. The spacing is the same, the order is the same, but the entire pattern has drifted toward the red end. As if someone gently tugged the whole strip sideways, that single slide is the redshift. Not a colour you notice, a displacement you measure. Now the formula, in plain words, because it is simpler than it sounds. You take the wavelength you observed, you subtract the rest wavelength you already knew. That gives you how far the line moved. Then you divide that gap by the rest wavelength, so the answer is a fraction rather than raw numbers. That fraction is what astronomers call z. A line that shifted 1/100th of the way gives a z of about 1/100th. A line whose wavelength has doubled, stretched to twice its resting length, gives a z of exactly 1. When you hear that a galaxy sits at z of 1, that is what it means. Its light arrived twice as long as it left. Push higher and the numbers grow stranger. A z of 14 means the light stretched to 15 times its original length while it travelled. Ultraviolet left the galaxy. Deep infrared arrived. The barcode is still readable. It has just been dragged an enormous distance across the spectrum. That measures the shift. It does not, on its own, tell you how far the galaxy is. For that you need a second kind of yardstick, and this is where the craft turns patient. The problem is that a faint smudge could be a dim thing nearby or a brilliant thing far off. Brightness alone lies to you, unless you already know how bright the object truly is. If you know an object's real output, its true luminosity, then how faint it looks tells you exactly how far away it must be. Light dims in a strict, predictable way as it spreads across distance. So astronomers hunt for objects whose true brightness they can know in advance. They call them standard candles. The first good candle was a kind of pulsing star. Cepheid variables swell and shrink in a steady rhythm, brightening and fading over days or weeks. And their rhythm is honest. The slower a Cepheid pulses, the more light it is truly pouring out. Time the pulse, and you have read the star's real brightness straight off its heartbeat. Compare that to how faint it looks in the sky, and the distance falls out. A slow, calm pulse for a bright star. A quick flutter for a dim one. The clock tells you the truth the eye cannot. Cepheids are wonderful, but even the brightest fade from view across the deepest gulfs. So for the far reaches, astronomers reach for something violent. A type Ia supernova is the death flash of a certain kind of collapsing star, and these detonations are almost eerily uniform. They ignite at very nearly the same peak brightness every time, like matched bulbs scattered across the cosmos. One of them can briefly outshine an entire galaxy. Because you know how bright the flash truly was, you can read its distance from how faint it appears, even billions of light years out. Picture the whole arrangement as a ladder. The bottom rungs are close and solid, calibrated against stars whose distances we can nail down directly. Cepheids form the next rungs up. Type Ia supernovae reach higher still, into galaxies far too remote for any pulsing star to be seen. Each rung is set by trusting the rung beneath it. You climb one careful step at a time, and every step has to hold because the rung above depends on it. Kick out a lower rung, and the whole ladder wobbles. So now you have both halves of the measurement. The redshift, reads straight from the shifted barcode, tells you how much the light has stretched. The standard candles climbed rung by rung tell you how far the light has come. Put the stretch against the distance, and you can start to ask how fast space itself is opening up. But there is a complication hiding in that stretch, and it took a beautiful experiment on Earth to prove it real. Not all reddening comes from things flying apart. Light also loses energy simply by climbing out of gravity. Fall into a heavy object and light gains energy, shifting bluer. Climb away from one and it pays a toll, shifting redder. This is gravitational redshift, and for a long time it was only theory, far too faint to catch in ordinary conditions. In 1959, two physicists at Harvard caught it anyway. Robert Pound and Glenn Rebka sent gamma rays up and down a tower on their own campus, a rise of only a few dozen feet. That is nothing against the pull of the whole Earth. Yet, by tuning their instruments to a razor's edge, they measured the tiny energy the gamma rays lost climbing up the tower and gained falling back down. The shift was almost unimaginably small. They found it exactly where Einstein said it would be. Light bled a sliver of energy just from rising through Earth's gravity. On a single quiet tower, they proved that gravity reddens light, right here at home. That result matters for reading the sky, because it means a redshift can carry more than one story. Part of a galaxy's shift might be motion. Part might be the pull of the mass it sits inside. If you want the honest expansion signal, you have to separate the two, and that is the practical craft that made redshift trustworthy. Inside a dense cluster of galaxies, both effects are present at once. The galaxies swarm, some drifting toward you, some away, which adds ordinary motion in both directions. But the deep gravity of the cluster adds a one-sided tint. Gravitational reddening never shifts anything blue, it only pushes toward the red. So the two leave different marks. Random motion scatters the redshifts evenly around a center, spreading them symmetrically to either side. The cluster's gravity nudges the whole center of that spread slightly redward. Measure enough galaxies, watch where the middle of the distribution sits versus how the scatter fans out around it, and you can tease the gravitational part away from the pure motion. No single galaxy confesses this. The crowd does, statistically, once you gather enough of them. That patience is the whole reason redshift became something to trust rather than something to argue about. Every piece was checked against something we could hold still. The rest wavelengths came from gas in a laboratory. The candles were calibrated on the closest rungs first. The gravitational shift was pinned down on a tower you could walk up. Piece by piece, the tool was built to survive doubt, and once you trust it, the shifted barcode in every distant galaxy becomes a number you can act on. Read the stretch, climb the ladder for the distance, correct for gravity where it hides. Out the other end comes a value for how fast the space between galaxies is unfolding. Do it for one galaxy, then 100, then thousands, and a rate begins to emerge, a single number meant to describe how quickly the whole universe is growing. The trouble is that when we try to measure exactly how fast that stretching happens, the universe hands us two different answers. The trouble is that when we try to measure exactly how fast that stretching happens, the universe hands us two different answers, not two rough guesses that overlap around the edges, two firm, well-measured numbers that refuse to agree. And the strange part is which measurements they come from. Both are careful, both are trusted, both have been checked and rechecked by different teams using different instruments, yet they land in different places and they stay there. Start with the nearby method. Astronomers look at the recent local universe, the part close enough to study star by star. They find a special kind of star called a Cepheid variable. A Cepheid pulses, brightening and dimming on a clock so regular that its rhythm reveals its true brightness. Compare that true brightness to how faint it looks from here, and the distance falls out. That gives you a ruler. Then they reach further, using exploding stars called type Ia supernovae, each one detonating at nearly the same brightness, like a matched set of flares laid out across the cosmos. Stack these rulers end to end, measure how fast those galaxies are receding, and you get a number for the expansion rate. That number comes out near 72 to 74. The full units are kilometers per second per megaparsec, and it helps to slow down and say plainly what a megaparsec is. A parsec is a distance astronomers use, and a megaparsec is a million of them. In more familiar terms, 1 megaparsec is about 3.26 million light-years. So this measurement says that for every 3.26 million light-years you look further out, galaxies rush away roughly 72 kilometers per second faster. Push out another megaparsec, add another 72. That is the local answer. It is built from things you can almost point to, stars you can watch pulse, explosions you can time. Now take the other method. Instead of nearby stars, it uses the oldest light there is, the faint afterglow of the young universe, released when the cosmos was only about 380,000 years old. A glow that still washes over the whole sky today. The Planck satellite mapped that ancient light in exquisite detail. Inside its faint ripples is a record of how much matter there was, how fast space was pushing outward, and how the whole thing should have evolved from then until now. Run that early snapshot forward through the standard model of cosmology, and you can predict how fast the universe ought to be expanding today. That prediction comes out near 67.4. Same units, same universe, a completely different starting point. One number is read off nearby stars in the recent universe, the other is inferred from the infant cosmos and carried forward across 13.8 billion years, and they miss each other, not by a rounding error, by a gap that has held its ground no matter how hard people try to close it. Before we go further, take a breath. If you enjoy having the strangest corners of the cosmos read to you like this, a quiet like or subscribe helps these long nights reach other people who fall asleep to them. That is all. Now settle back in. This disagreement has a name. Cosmologists call it the Hubble tension, after Edwin Hubble, whose work first tied recession speed to distance. And the word tension is doing polite work there. What it really describes is two answers that will not reconcile. To measure how serious a mismatch is, scientists count in units of sigma. 1 sigma is ordinary scatter, the kind of wobble you expect in any measurement. 2 or 3 sigma is worth a second look. 5 sigma is the line physicists draw for a genuine discovery, the point where a result is far too large to blame on luck. The Hubble tension, in many careful analyses, now exceeds 5 sigma. That means the odds of it being a random fluke are vanishingly small. The two numbers are not brushing shoulders by accident. They are genuinely, stubbornly different. Here is the part that should stop you cold. When two measurements disagree, the natural expectation is that better instruments will fix it. Sharper tools, cleaner data, and the gap narrows until it closes. That is how science usually resolves an argument. The two sides drift toward the middle and meet. With the Hubble tension, the opposite has happened. The better the telescopes have gotten, the wider the gap has grown. Think about how backward that is. You buy a more precise ruler expecting your two conflicting measurements to converge. Instead, they pull apart. That is not what a simple mistake looks like. That is what it looks like when something real is missing from the picture. The most recent years have driven the point home. The James Webb Space Telescope, the sharpest eye humanity has ever built, went to work checking those nearby Cepheid stars. If the local high number were an artifact, some blur or crowding in older images, Webb was the instrument to expose it. It did the opposite. Webb's observations reinforced the high local value. The nearby ruler held. Around the same time, a project called DESI, the Dark Energy Spectroscopic Instrument, went after the other end. DESI reinforced the low, early universe value. So the two best modern efforts did not meet in the middle. Each one dug its own side of the trench deeper. As of the 2025 and 2026 status reports, the gap has held or widened. Nobody has closed it. Cosmologists do not use the word crisis lightly, but many of them use it here. Picture two rulers built from entirely different materials. One is carved from nearby stars in the living present. The other is cast from the faint 13.8 billion-year-old glow of the beginning. They are both measuring the same single universe. They should print the same number on the page. They simply do not. And the harder you look, the more certain you become that the disagreement is real rather than sloppy. Then, while that argument was already burning, Deci delivered a second shock, and this one struck at something even deeper. Deci did more than measure the expansion rate. It built the largest three-dimensional map of the universe ever made. Nearly 15 million galaxies and quasars, their positions charted across billions of years of cosmic history, laid out like beads scattered through a vast, dark room. With a map that big, you can do something remarkable. You can watch how the push of expansion has changed over time. Everyone assumed the answer was already known. The force driving galaxies apart is called dark energy, and in the standard model it is treated as a constant, a fixed property of empty space itself, the same strength yesterday, today, and forever. That assumption sits at the very centre of the theory. It even has a symbol, the cosmological constant, the same idea Einstein once bolted onto his equations for entirely different reasons. Deci's map hinted that the constant might not be constant. The data suggests dark energy may have been stronger in the distant past and may be weakening as time goes on, fading, slowly, over billions of years. This is not yet a settled result, and honesty matters here. The statistical confidence sits somewhere between 2.8 and 4.2 sigma, depending on which datasets you combine. That is genuinely striking. It is also short of the 5 sigma line that turns a hint into a discovery. So this is not proven. It is a signal, growing, that serious people cannot dismiss and cannot yet confirm. Sit with what it would mean if it holds. If dark energy is truly evolving rather than fixed, then the cosmological constant at the heart of the standard model is wrong, not slightly off, wrong in its core assumption. And the uncomfortable truth is that physicists do not have a finished replacement waiting in a drawer. There is no rival theory ready to step in and explain a dark energy that changes with time. You would be tearing out the keystone of modern cosmology without knowing what holds the arch up next. That is a rare and vertiginous position for a science to find itself in. The best map ever made is quietly suggesting the foundation might be cracked and offering no blueprint for what comes after. So what could be going on? The candidate explanations are all still live, and none of them has won. Sit with them one at a time because each is its own strange possibility. The first is almost cozy. Maybe our own corner of the cosmos is unusual. Imagine that the Milky Way happens to sit inside a large region that is slightly emptier than average, an underdense bubble, a local void. Inside such a void, nearby galaxies would be tugged outward toward the denser region surrounding it, and that gentle pull would make the local expansion look faster than the true cosmic average. If that were the case, the high nearby number would be a trick of our address, not a property of the whole universe. It is a tidy idea. Whether the void is real and deep enough to do the job is still argued. The second explanation is the humble one, the one careful scientists always keep on the table. Maybe there is a hidden systematic error. Not a random wobble, but a consistent lean in one of the methods that nobody has caught yet. A subtle bias in how Cepheid brightness is calibrated, or something buried in the early universe analysis. Systematic errors are slippery precisely because they do not look like mistakes. They look like clean, confident answers that happen to be tilted. The whole reason Webb went to check was to hunt for exactly this, and so far the tilt, if it exists, has not been found. The third explanation is the thrilling and frightening one. Maybe both measurements are right, and the universe really is telling us something we do not yet understand. New physics, hiding in the dark sector, the shadowy pairing of dark matter and dark energy that together make up the overwhelming majority of everything, and that we grasp the least. If that is the answer, the Hubble tension is not a bug in our measurements. It is the first clear crack in the standard model, the place where a deeper theory is trying to show itself. And here is the fact that should keep you humble under all of it. Dark energy, the thing blamed for the acceleration, the thing Deci now hints may be weakening, has never once been detected directly. No instrument has ever caught it, bottled it, or measured it on a bench. Its entire existence is inferred. We know it only by its effect, the way it makes the redshifts of distant galaxies larger than gravity alone could ever explain, the way everything is rushing away faster than a slowing, matter-filled universe should allow. We named a force after a fingerprint. We have never seen the hand. Take a moment with how deep that goes. Roughly 70% of the entire universe, by the standard accounting, is made of a substance we cannot see, cannot touch, and cannot produce. We infer it purely from stretched light and accelerating distances, and now our best map suggests that even our description of that invisible majority may be wrong. This is the honest state of the field. Two rulers that will not agree past 5 sigma, a dark energy that might be fading at 4 sigma, and beneath both, a component of reality we have only ever met as a shadow on the wall. None of this means the science is broken. It means the opposite. It means the tools have gotten precise enough to reveal a problem that cruder instruments could hide. A century ago, the discovery was simply that the universe expands at all. Now the frontier has moved to a far subtler question. Not whether space is stretching, but exactly how fast, and whether the force behind it is steady or slowly changing its mind. The disagreement is not a failure of measurement. It is a measurement so good that it has outrun our theory. And notice what these rulers are actually made of. Every one of them is built from redshift. The nearby ruler reads the redshift of supernova in the recent universe. The early ruler reads the imprint left in the oldest light of all. Both are decoding the same single clue, that faint reddening stamped onto starlight by expanding space. The tension is really an argument about what that reddening means when you read it near versus far, now versus long ago, which turns the whole question inside out. To measure the expansion rate at all, you are never just measuring distance, you're measuring time. And the further out you push that measurement, the deeper into the past you're actually staring. And the further out you push that measurement, the deeper into the past you're actually staring. Redshift is not only a ruler for distance, it is a dial for time. Turn it higher and you wind the universe backward. A galaxy at redshift 1 shows you light that left when the cosmos was roughly half its present size. Push the number further and you are no longer looking at a place, you are looking at an age. Every increase in that stretch is a step toward the beginning, toward a younger, hotter, denser sky. Hold that idea gently for a moment. The colour of old light carries a timestamp. The redder it arrives, the earlier it was born. So the deepest images we have are not really pictures of far-off things. They are pictures of long-ago things. The same measurement that tells you how far tells you how long. And the universe, it turns out, keeps almost nothing hidden from that dial except the very first instant. Follow the dial as far as it will go and eventually you hit a wall. Not the edge of space. A wall of light. It is the oldest glow we can see, and it comes from every direction at once. Astronomers call it the cosmic microwave background. It left its source at a redshift of about 1100. That number means the light has been stretched more than 1,000-fold on its way to you. It set out when the universe was only about 380,000 years old. Think about how young that is. The cosmos today is 13.8 billion years old. 380,000 years is the first thin sliver of that story, a single early breath. And at that moment the whole universe glowed at around 3000 Kelvin. That is close to 4,940 degrees Fahrenheit. Everywhere. Not one hot star in a cold sky. The entire sky was that temperature edge to edge. Why does that glow mark a wall? Because before it, the universe could not be seen through at all. It was opaque. Picture a fog so thick you cannot see your own hand in front of your face. That is what the early cosmos was like to light. It was too hot for atoms to hold together. Electrons roamed free, unbound, everywhere. And free electrons are ferocious at scattering light. A photon could not travel in a straight line. It bounced again and again, deflected almost the instant it set out. The universe was a glowing fog with no clear view across it. Then something changed all at once, everywhere. As the universe expanded, it cooled, and when it dropped to that 3000 Kelvin mark, the free electrons finally slowed enough to be captured. They joined with protons and settled into the first stable atoms. Astronomers call this recombination, though it was really the first combination. The moment it happened, the fog lifted. Light that had been trapped, scattering endlessly, was suddenly free to fly in a straight line across open space. Imagine standing inside a cloud so dense it presses on your eyes, and then in an instant the whole cloud clearing at once in every direction, forever. That is the surface of last scattering. It is not a place with a wall. It is a time when the universe became transparent. The last light to scatter off those vanishing electrons set out on a journey that is still arriving. You are being touched by it right now. Here is the part that should stop you cold. That light left when the sky was hotter than a furnace, glowing at thousands of degrees, but it does not reach you hot. It reaches you as one of the coldest things you can measure. 13.8 billion years of cosmic expansion has stretched those waves out enormously. The glow that began at 3000 Kelvin now arrives at about 2.7 Kelvin. That is roughly 454.8 degrees below 0 Fahrenheit. The fire of the young universe, cooled by expansion into a faint microwave hum, and it comes from a shell that now sits nearly 45 to 46 billion light-years away. That is the present distance to the material that emitted the glow you're catching tonight. The light is old. The place it came from has been carried much further out by the expanding space in between. You cannot see past that shell with ordinary light. It is the fog, frozen at the instant it lifted, the oldest photograph the universe allows. Before we push closer to the beginning, take one small moment for the channel. If this slow unwinding of cosmic time is holding you, a like or a subscribe helps more people find these long nights, and you can find us on Spotify too. That is all. Now settle back and let us turn the dial further. Between that ancient fog and the galaxies of today lies a long dark stretch, and then the first stars catch fire. The deepest galaxies we have ever confirmed are burning right at that early edge, and the current record holder has a name that reads like a coordinate, MZ14. Its redshift is measured at 14.44. The James Webb Space Telescope caught it, and when you decode that number back into time, it tells you something almost unbelievable. You're seeing that galaxy as it was just 280 million years after the Big Bang. Let that settle. The universe was less than 300 million years old. Not 3 billion. Less than 300 million. That is a toddler stage for a cosmos that would go on to run for 13.8 billion years and counting. And already there is a galaxy there, assembled, bright enough to see across the entire span of cosmic history. MZ14 took the crown from another record holder, one you may have heard named before, Jade's GS Z14-0. That galaxy sits at a redshift of about 14.32, though you'll find it listed in some sources as 14.18, a small disagreement between press releases that comes with measurements this delicate. It was confirmed in early 2024, after nearly 10 hours of the telescope staring at a single faint smudge with its spectrograph. 10 hours of collecting light to pin down one number. That patience placed the galaxy at roughly 290 to 295 million years after the beginning. Picture what you're actually looking at when that light finally lands, not a grand spiral like the ones on posters. a hot, chaotic, still assembling knot of young blue stars packed close, blazing hard in a universe that had barely begun, its light left as visible and ultraviolet glow. By the time it crosses all that expanding space and reaches the telescope, it has been stretched deep into the infrared. The blue fire of the infant cosmos arrives dressed in a colour the eye cannot even see. And here is the anomaly that keeps astronomers up at night. These galaxies should not be so bright so soon. The models of how galaxies form predicted far fewer of them at this early hour, and far dimmer. There simply should not have been enough time for so much starlight to gather this fast after the Big Bang. Yet every time the telescope pushes the record earlier, it finds another one that looks too big and too developed for its age. The problem does not go away with better data. It gets reconfirmed. The early universe, it seems, built its first galaxies faster than our theories allow. You can feel the tension in that. A tool as trusted as Redshift, decoding light with almost perfect confidence, keeps handing us a picture that our best models cannot explain. The measurement is not in doubt. The galaxies are really there, really that early, really that bright. It is the story of how they got there so quickly that is broken, and a broken story in science is not a failure, it is a door. Now hold both ends of this at once. The oldest light, the cosmic fog, from 380,000 years in, the oldest galaxies from 280 million years in. Both reach you as faint, stretched, reddened whispers. Both are time machines. When you look at MOMSI 14, you're not seeing a young galaxy sitting far away in the present day. You're seeing the universe as it genuinely was when it was less than 300 million years old. That galaxy is not young anymore. It has had 13.5 billion years to grow, to churn through generations of stars to become something else entirely. But that later self is invisible to us. Its news can never reach us. We are locked to the version of it that set out long ago. Which brings us to the strangest geometry of all. If the universe is 13.8 billion years old, you might expect that the furthest we could ever see is 13.8 billion light years. Light travels 1 light year per year, so in that much time, it crosses that much distance. It seems airtight, and it is completely wrong. The observable universe stretches about 46 billion light years in every direction. That is a radius. End to end, the sphere we can observe is roughly 93 billion light years across, from a cosmos not yet 14 billion years old. The numbers do not match, and the mismatch is not an error. It is the signature of expanding space. Here is why. When that ancient light set out, the source was close, but space did not sit still while the light travelled. It expanded the whole way. Every mile the photon crossed, the road behind it and ahead of it kept stretching. So the object that emitted the light has been carried far beyond where it was when it emitted it. The light logged 13 billion years of travel time, but the ground it covered kept growing under it, and the source drifted out to 46 billion light years of present distance. Picture a swimmer who has been in the pool for 1 hour, moving at a steady pace. You would expect them a fixed distance from the wall. But the pool itself has been growing the whole time, the far walls sliding away as they swim. After an hour, they are much further from that wall than an hour of swimming should ever allow. The water carried them. That is expanding space, and that is why a young universe can be so astonishingly wide. Now sit with the consequence. Some of the galaxies you can see right now, tonight, in the deepest images ever taken, are already more than 46 billion light years away in real, present distance. Their old light reached us. But they have been carried so far by the expansion that any new light they send today will never arrive. Not in 1 billion years, not ever. We can see their past. We can never see their present, and we never will again. The connection is already severed, even as their ancient glow still lands on the mirror. That is the quiet knife edge of Redshift as a time machine. It shows you the deep past in exquisite detail, the fog at 380,000 years, the first galaxies at 280 million, a sky 93 billion light-years wide. And in the very same breath, it tells you that much of what you are seeing is a farewell. The light is a message from objects that have already slipped beyond any possible reunion. You're reading letters from friends who moved away so far and so fast that no reply can ever reach them. So the dial that lets us look earliest is also the dial that counts down. The higher the redshift we chase, the more of the universe we find already drifting past the point of no return. We are catching the ancient light at the last moment it is still catchable. Think about the machines that actually catch this stretched light. They are not abstractions. They are real instruments, with names and cold numbers, sitting in dark places and staring outward for hours at a time. Each one is built to read the same faint signal, and each one carries its own record and its own quiet argument about how fast the universe is flying apart. Start with the James Webb Space Telescope. Its gold mirror is wide and patient, a net dipped into a slow stream of light that has been falling toward it for billions of years. Behind that mirror sits an instrument called NIRSPEC, the Near-Infrared Spectrograph. Its task is simple to say and hard to do. It spreads incoming light into a spectrum. Then it hunts for the fingerprints of elements like hydrogen, and it measures how far those fingerprints have slid toward the red. In January of 2024, that instrument settled on a faint smudge called JADIS GS ZSZUL 14-0. It stared at that one smudge for almost 10 hours. 10 hours of quiet counting, gathering light one grain at a time. When the numbers came back, the galaxy sat at a redshift near 1432. That means its light left home when the universe was only about 290 to 295 million years old. Let that figure rest against you for a moment. The universe is 13.8 billion years old now. This galaxy shows you a moment less than 300 million years in. You're watching the infant cosmos, held still in a single long exposure. And here is the strange part. The stars in that galaxy were burning hot and blue. Yet by the time their glow crossed all that expanding space and reached the mirror, it had been stretched so far that it arrived as infrared. The true blue was reddened out of sight before the telescope ever caught it. Webb does not see the colour those stars actually had. It sees the ghost of that colour, pulled long by the growing distance. That record did not stand for long. By 2025, a fainter and even older object took the title. Astronomers named it MOMZ14, and they pinned it at a redshift of 14.44, confirmed and written up in the Open Journal of Astrophysics. Its light left when the universe was roughly 280 million years old. A few million years earlier than the last champion. That may sound like a rounding error, but at these depths, every step backward is enormous. Each new record pushes the eye closer to the beginning itself. And each record deepens a small crisis. Nobody expected galaxies this bright to already exist this early. The model said the young universe should not have had time to build something so large and so luminous so soon. Yet Webb keeps finding them anyway. Too big, too bright, too early. The telescope was meant to confirm the story of how galaxies grew, and instead it keeps handing back objects the story cannot quite explain. Now step back from the record chase and think about a very different machine. Before Webb there was the Planck satellite. It was not built to find single galaxies at all. It was built to map the oldest light in existence, the faint afterglow left over from when the universe was about 380,000 years old. That glow fills the whole sky, coming from every direction at once, a smooth wall of cooled radiation now sitting near 2.7 Kelvin. Planck spent years measuring the tiny ripples in that wall. From those ripples, cosmologists worked backward to the early expansion rate of the universe. They pinned it near 67.4 kilometers per second per megaparsec. That number is a kind of speedometer, reading taken from the dawn of everything, drawn out of a 13.8 billion-year-old signal. It is one of the most carefully measured numbers in all of science, and it is the source of a deep unease, because when you measure the same expansion using nearby stars instead of ancient light, you get a faster answer. Two honest rulers, built from two different eras, refusing to agree. Then there is the newest of the great readers, and in some ways the most staggering to picture. The dark energy spectroscopic instrument called DESI. It does not stare at one faint smudge for 10 hours. It does the opposite. It drinks in thousands of galaxies at once, night after night, building something no one had ever built before. Picture the result as a vast dotted map stitched together from millions of separate pinpoints. Each pinpoint is a real galaxy, or a blazing quasar, placed in 3 dimensions by its redshift. The nearer ones sit close, the farther ones sit deep. In its second data release, DESI had charted nearly 15 million galaxies and quasars in this way. It is the largest 3-dimensional map of the universe ever made, a single chart holding more objects than any human eye could count in a lifetime, each one a place where the light has been reddened by the same relentless stretching. And that giant map carries its own quiet shock. When cosmologists studied the pattern of all those dots, the data began to hint that dark energy, the force driving everything apart, may not be a fixed constant after all. It may be slowly weakening over cosmic time. The signal is not certain yet. It sits somewhere between 2.8 and 4.2 sigma, short of the mark physicists demand before they call something a discovery. But it is building, not fading, as more of the map fills in. So look at what these 4 machines are really doing when you set them side by side. Webb catches individual grains of the earlier starlight so stretched they land as heat instead of colour. Planck reads the smooth afterglow of the whole young sky. DSE stitches millions of pinpoints into one enormous lattice. Different instruments, different methods, different corners of the same problem. Yet every one of them is measuring the same underlying thing. Every one of them is watching light that has been reddened by expansion and asking that redness a single question. How fast is it all pulling apart, and has that speed always been the same? The answers do not fully agree, and that disagreement is not a failure of the machines. These are the most precise instruments our species has ever pointed at the sky. NearSpec can hold a faint galaxy in view for hours without wandering. Planck mapped a signal cooled to less than 3 degrees above absolute zero. DESI logs galaxies by the 1,000 every clear night. When tools this careful still hand back numbers that clash, the clash itself becomes the discovery. Something in the story is missing, and the sharper the eye, the plainer that gap becomes. There is a strange comfort in it, if you let there be. Every one of these instruments is reading a message that was written long before Earth existed, in a language of stretched light that the universe never meant for anyone to read. And we learned to read it anyway. We built mirrors and spectrographs and vast dotted maps, and we taught ourselves to hear the falling pitch of the whole cosmos as it drifts away from us. Webb tells you how early. Planck tells you how it began. DESI tells you how it is changing even now. They all point the same direction, outward and backward and away. Each galaxy on that map is a little farther tonight than it was when the light left it, and a little farther still than the number on the chart admits. The instruments are not just measuring the universe, they are catching it in the act of leaving, and that is what makes the whole enterprise feel so urgent and so fragile at once. Everything these machines see depends on the light still being here to catch. The gold mirror, the ancient afterglow, the 15 million pinpoints, all of it rests on the fact that this reddened light is still arriving, still falling into our nets while we happen to be looking. For now the sky is full. For now the record galaxies keep getting older, the maps keep getting wider, the afterglow still hums from every direction at 2.7 Kelvin. You live in an age when the reading is still possible, when the instruments still have something to gather. The strangest part is that this window we are looking through is quietly, permanently closing. The strangest part is that this window we are looking through is quietly, permanently closing. Not with a slam, not with any sound you could hear. It closes the way a tide goes out, so slowly that no single glance could ever catch it moving. Yet, it is moving. Somewhere out there, right now, a galaxy is crossing a line it can never come back over. That line has a name. Astronomers call it the cosmic event horizon. It is not a wall. It is not an edge you could ever fly up to and touch. It is a distance. Beyond that distance, the space between you and a galaxy is stretching so fast that light can no longer cross it. The galaxy is not hiding. It is simply falling out of reach. Any light it sends toward you from this moment on will never arrive. Not in 1 billion years, not ever. Think about what that means for a single beam of light. It leaves a distant galaxy tonight, aimed straight at your eye. It travels at the fastest speed anything is allowed to travel, and it still loses. The road beneath it lengthens faster than it can run. The light moves toward you the whole time, and the whole time it falls further behind. It is a swimmer striking out for a shore that is being towed away faster than any stroke could ever close the gap. If that idea rattles you a little, that is the right response, and it is worth a moment before you let yourself sink into the dark. If these quiet walks through the universe help you sleep, a like or a subscribe helps this channel more than you know. We are also on Spotify, for the nights when you would rather only listen. Now, the first thing you probably want to ask is whether this breaks a rule. Nothing can move faster than light. You have heard that your whole life, and it is true. So how can a galaxy outrun a beam? The answer is the quiet key to this entire night. Nothing is moving faster than light through space. Not the galaxy. Not one star inside it. Every object out there drifts gently through its own small pocket of space, slower than light, exactly as the rules demand. It is the space itself that is stretching, and space is under no speed limit at all. Picture 2 ants on a rubber sheet. Each ant can only crawl so fast. That is their law, and they never break it. But if you take the sheet and pull it wider from every side at once, the ants rush apart far faster than either one could crawl. Neither ant has broken its own limit. The ground between them simply grew. That is the universe. The galaxies are the ants, space is the sheet, and the sheet is being pulled wider everywhere all at once without end. There is an older picture for the same truth. Imagine a loaf of raisin bread rising in a warm oven. Every raisin sits still in the dough, yet as the loaf swells, each raisin drifts away from all the others. No raisin is crawling anywhere. The bread between them is simply growing. Our loaf never stops rising, and it pulls the raisins so far apart so relentlessly that in time no raisin can ever see or touch another again. So no law is broken. A galaxy can recede faster than light, and Einstein sleeps soundly, because that recession is not a motion at all, it is a growing. The distance swells without anything travelling across it. Here is the figure that should stop you cold. Roughly 94% of the galaxies you can see in tonight's sky are already receding faster than light. Not someday. Now. Almost everything painted across the observable universe sits beyond that horizon at this very moment. You can still see them, which feels like a contradiction until you understand the trick. The light you're seeing is old. It left those galaxies billions of years ago, back when they were still close enough for their light to make the crossing. That ancient light is only now arriving. But nothing they send today will ever reach you. You are looking at a portrait that was mailed long before the road washed out. Sit with that for a moment. 94 out of every 100 galaxies in your sky are places you can only ever see as they were. They are already unreachable. You could never travel to them. You could never send a signal that lands. You could never receive a single reply. They are visible ghosts glowing with light that outran the closing door just in time. And every year a few more of them slip past the frame and go quiet for good. The universe is slowly compartmentalizing itself, sealing each island off from all the rest, one galaxy at a time. This is why everything is rushing away. Not because the galaxies scorn us, not because we sit at some cursed centre, but because the sheet keeps stretching, and the stretch keeps speeding up. Dark energy, the thing no one can explain, presses on the whole sky and pushes it apart a little harder every day. And the further a galaxy already sits, the more stretched space lies between, and the faster it flees. Distance feeds the flight. The flight feeds the distance. The process only accelerates. Which raises the question that turns this from a lecture into something closer to a long farewell. If the horizon keeps swallowing galaxies, what does the sky look like in the deep future? Not 1,000 years from now, not 1,000,000, try 100 billion. A physicist named Abraham Loeb at Harvard has worked the arithmetic on that far tomorrow, and the picture he draws is one of the loneliest ideas in all of science. In roughly 100 billion years, he finds, almost nothing will be left to see. The galaxies not bound to us by gravity will have crossed the horizon and vanished. Their light will have stretched so far toward the red, grown so thin, so faint, that no instrument could ever pull it back out of the dark. One by one, over the long ages, they redshift into silence. What remains? Only the galaxies close enough that gravity still holds them in its grip. Our own Milky Way, and Andromeda, and the small huddle of nearby galaxies we call the local group. By then those will not even be separate places. Gravity will have drawn them together into a single vast island of stars, one merged remnant drifting alone. And around that island, in every direction you could ever aim a telescope, there will be nothing. No other galaxies, no smudges of distant light, just black and more black, out to the very limit of sight. Now imagine an astronomer born onto a world inside that far future island. She looks up. She sees her own galaxy of stars, calm and unchanging, and beyond it she sees only empty night. She builds telescopes as fine as ours, finer. She points them into the dark, and the dark stays dark. There are no other galaxies to find. There is no drift to measure, no redshift survey to run, because there is nothing out there left to shift. She would have no way to know the truth. From everything her eyes and her instruments could gather, her single island of stars would appear to be the entire universe, static and eternal, floating in a void that was always empty. The Big Bang would be invisible to her. The expansion would be undetectable. The whole grand story of a cosmos that began small and hot and blew outward for billions of years would be gone, erased, with no trace left in her sky to read. And here is the cruelest detail. She would even lose the oldest clue of all. The faint afterglow of the beginning, the cosmic microwave background, that whisper of warmth filling our own sky from every direction, would itself have stretched away. Cosmic expansion would redden it and dim it until it faded below anything she could detect. The one piece of evidence that survived from the very first moments, the light we still read today, would slip past her horizon too. She would inherit a universe with its own birth certificate quietly torn out. So she would conclude, reasonably, carefully, and completely wrong, that her island was all there ever was. Not out of foolishness, out of an honest reading of an empty sky. The universe will have hidden its own history from her, and left her no way to even suspect the theft. You and I do not live in that era. We live in the narrow window while the door is still open, while the light of a young cosmos still pours in, while the evidence still lies scattered across the sky for anyone patient enough to look. That is a strange kind of fortune. We may be closer to the last age when the universe is knowable than to the first. Loeb, though, is not a man who accepts a locked door without testing the hinges, and he offered one thin, ingenious thread of hope for those far future watchers. It rests on a peculiar kind of star. Sometimes a star gets flung out of its galaxy entirely. It passes too close to something violent, a black hole at the galactic centre, a slingshot of gravity, and it is hurled outward at tremendous speed, cast off into the emptiness beyond the galaxy's edge. Astronomers call these hypervelocity stars. They are runaways, exiles, thrown clear of everything they were born into. Loeb's idea is that these exiled stars could become lampposts. As the far future island floats alone, its own hypervelocity stars would go sailing out into the surrounding dark, carried further and further by the very expansion that hid everything else. And if that astronomer watches those departing stars closely, if she measures how their light reddens as they recede, she could read the stretch of space in their glow. The stars she can still see, still bound to her by nearness, could carry the fingerprint of an expansion she can no longer observe any other way. A handful of thrown stars acting as messengers, whispering that the void is still growing after all. It is a slender hope. A few faint lamps against an ocean of black. Whether any civilization out there would ever think to look, or believe what the lamps were telling them, no one can say. It may be that the universe leaves that one last clue behind, and it may be that no one is ever there to read it, and that is the quiet wait this whole night settles into. The sky above you is a document. It is written in redshift, in stretched light, in the slow reddening of distant fire. Every galaxy you can see is a line in that document, a record of a cosmos that began and grew and is still growing now. We can read it. We are perhaps among the last who ever fully will. The lines are fading, one by one, drifting past the edge of what any eye or lens can ever hold. Not everyone trusted the yardstick. For a tool this powerful, that resistance was healthy, and it lasted for decades. Its most stubborn doubter was an American astronomer named Halton Arp. He was not a crank on the fringe. In 1966 he compiled the Atlas of Peculiar Galaxies, a catalogue of the strangest galaxies anyone had photographed. Picture that atlas as a stack of warped portraits, turned one page at a time. Galaxies with tails, galaxies with bridges of light strung between them, galaxies bent and torn and colliding. Arp had spent his life staring at the objects that refused to behave, and that habit shaped everything he came to believe. By 1987 he had turned that habit into a heresy. In a book called Quasars, Redshifts and Controversies, he argued something close to unthinkable. He claimed that some quasars with enormous redshifts sat right beside nearby galaxies with tiny redshifts. Not by accident, he said, but connected, physically linked, tied together by faint threads of gas and light. Sit with what that would mean. A quasar might show a redshift that says it is billions of light years away. The galaxy it seems to touch might show a redshift that says it is close. If the two are genuinely joined, they cannot be at wildly different distances, and if they are not, then redshift is lying about at least one of them. The whole foundation would crack. Redshift would no longer be a clean ruler for distance. It would be something murkier, something local, something you could not trust. That was the danger Arp represented. He was not saying the universe was slightly off. He was saying the measuring stick itself was broken. He was not alone, and he was not the stranger's voice. Some astronomers went further. They claimed that galaxy redshifts did not spread out smoothly at all. Instead, they said, the numbers clustered around certain preferred values, as if the universe only allowed a fixed menu of speeds. The favoured notches fell near 0.061, then 0.3, then 0.6, then 0.9 to 1, then 1.4 to 1, then 1.96. They called it redshift quantization. Imagine a ratchet, the kind of gear that clicks forward and locks into fixed teeth. That was the picture. The idea that galaxies did not drift away at any old velocity, but snapped into slots, one click, then the next, then the next. If that were true, it would be impossible to explain with simple expansion. Expansion should give you every value in between, a smooth continuum with no gaps and no favourites. A ratchet with fixed teeth is a machine, and a machine hiding inside the redshifts of galaxies would have meant a century of physics had missed something enormous. You can feel why these claims made people uneasy. They were specific. They came with numbers. They came from a respected observer holding real photographs. For a while, the pattern seemed to hold in the small sets of galaxies that had been measured, and a strange mechanical regularity is exactly the sort of thing that keeps a scientist awake, because if it is real, everything downstream has to be rebuilt. So the field did the only honest thing. It went and looked harder. The answer came from size. The early quantization claims rested on a few hundred galaxies, sometimes fewer. Small samples are treacherous. In a small sample, clumps appear out of pure chance, the way a handful of thrown coins can land in a row and mean nothing at all. When astronomers gathered redshifts for tens of thousands of galaxies, then hundreds of thousands, then millions, the notches dissolved. The clicks smeared into a smooth flow. The ratchet had no teeth. It had never had teeth. The pattern had been an artifact of too little data and hopeful arithmetic, and it melted the moment the data grew. ARP's linked quasars fell the same way. Put two objects close together in the sky, and some of them will line up by pure coincidence because the sky is deep and crowded. A quasar behind a galaxy is not touching it. It is simply behind it, far away, its light passing the nearer galaxy on the way to you. As the surveys grew and the statistics sharpened, the apparent connections thinned into chance alignments. The bridges ARP thought he saw did not survive careful counting. There was a gentler alternative floating through those same years, and it deserves a fair hearing. It was called tired light. The idea was almost soothing in its simplicity. Maybe space is not expanding at all. Maybe a photon just loses a little energy on its long journey, worn down by some quiet interaction with the emptiness it crosses. Travel far enough and the light reddens, not because the universe grew, but because the light grew tired. No expansion required, no fleeing galaxies, just a slow, gentle fading across distance. It is a lovely thought, and it is wrong. The proof came from exploding stars. A certain kind of supernova brightens and fades on a known schedule, like a clock you can read across the cosmos. If the universe is truly expanding, then a distant supernova should appear to run in slow motion, its whole light curve stretched out in time, the same way its light is stretched in wavelength. And that is exactly what astronomers see. A supernova at high redshift takes visibly longer to rise and fall, its clock slowed in precise step with its colour shift. Tired light cannot do that. Photons losing energy would redden the light, yes, but they would not slow the clock. They would not stretch the days of an explosion into weeks. Only real expansion does both at once, and the sky shows both at once. So tired light joined the ratchet in the drawer of ideas that were tested and did not hold. ARP himself never surrendered. To explain his anomalies, he reached for a final idea, one he called intrinsic redshift. He suggested that redshift might reflect an object's age or its inner nature, some property built into the thing itself, rather than its motion or its distance. A young quasar in his telling might simply be born red. It is a striking notion, but it never passed the one test that matters. No one could reproduce it under controlled measurement. No independent method confirmed it. It explained the puzzles he wanted explained and nothing else, and a theory that only fits the cases it was built for is not yet knowledge. It stayed on the margins, cited by a few, set aside by nearly everyone, a rejected chapter rather than an open question. It would be easy to tell this as a story of a stubborn man who was simply wrong, and in the narrow sense he was. But that is not the useful lesson. The useful lesson is what the challenge did to the tool. Redshift was not handed down as scripture, it was attacked. It was attacked by a skilled observer with real photographs and real anomalies for decades, in print, in public, with specific numbers that could have brought the whole framework down. And instead of being defended by authority, it was defended by data. Larger surveys, sharper statistics, the slow clock of distant supernovae. Every serious objection was met not with dismissal, but with more measurement, and the tool came through each test still standing, sharper than before. That history is why you can trust what Redshift tells you now. And it is why the deepest present puzzle is taken so seriously rather than waved away. When two careful measurements of the expansion rate refuse to agree, and the gap holds firm past 5 sigma even as the instruments improve, no one shrugs and calls it noise. They remember Earp. They remember that this yardstick has already been dragged to the breaking point once and did not break, so when it strains again, the field leans in, because a tool that survived that trial does not lie for no reason. There is a quiet weight in all of this. Redshift earned its authority the hard way, through argument and evidence and the patient defeat of every alternative. It became the thread that ties the whole story together, the colour shift that tells you the cosmos is flying apart. And yet the very expansion it measures is slowly carrying the evidence away. The distant galaxies that let us test these ideas are receding, reddening, thinning toward the edge of what any instrument can catch. The supernovae that broke tired light, the surveys that dissolved the ratchet, the linked-looking quasars that turned out to be chance, all of it depends on a sky still crowded enough to argue over. The heretics lost their case because the data was rich enough to convict them, but the richness is not permanent. The same expansion that Arp doubted is emptying the sky that proved him wrong. Every century, a little more of the record drifts past the horizon and out of reach. The debate could only happen because we can still see enough to have it. One day all of that evidence will be gone, and there will be no one left who could ever have known. One day all of that evidence will be gone, and there will be no one left who could ever have known. Sit with that for a moment. The soft microwave glow that fills the sky in every direction will have stretched too far to catch. The other galaxies will have slipped one by one over the edge of what can be seen. An astronomer standing where you stand 100 billion years from now will look up into a sky with a single island of light in it. That island is our own galaxy, merged with its nearest companions into one quiet smear of stars. To that watcher, that lone glow will look like the whole of creation, still and closed and eternal, and nothing they can measure will tell them otherwise. It began, all of it, with a colour, a faint reddening in the light of a distant thing. For a long time you might have thought a colour was just a colour, a fixed property stamped onto starlight the way a name is stamped onto a coin. It is not. That reddening was the universe speaking in the only language it has. It was telling you that the space the light crossed had been growing the entire way. It was telling you the cosmos is not fixed. It is expanding, and the expansion is speeding up, and it is quietly carrying every distant galaxy away from every other one, forever. Here is the strange heart of it, one last time. When you say a galaxy is fleeing from you, you picture something moving, engines lit, tearing across the void. That is not what is happening. The galaxy is, for the most part, sitting still. It is the room around it that keeps getting larger. New distance is being made in the gap between you, mile after mile after mile, and that new distance is what pushes the two of you apart. That is why the far ones can recede faster than light without breaking a single rule. Nothing is racing through space. Space itself is the thing that grows. So when you feel that everything is rushing away, understand what the words really mean. Nothing is rushing. The rushing is the space. That single idea rearranges your place in time. You happen to be alive in the one window when the sky still holds enough evidence to piece the story together. The other galaxies are still close enough to see. Their light still carries the tint that gives the whole game away. Every civilization that comes after this era will inherit a poorer sky, a little emptier, a little more silent, with a little less written across it. You are not standing near the dawn of the knowable universe. You are standing closer to its dusk. The clearest view there will ever be is roughly the one above your roof right now, and it is very slowly draining away. There is a strange comfort tucked inside that thought. You were handed a rare seat. The colour in the starlight is a message that will not always be legible, and you were born early enough to read it. The cold afterglow of the beginning still washes over the Earth every second of every night. The most distant galaxies ever found still hang in the record, their light set out when the universe was a few 100 million years young. All of it reaches you now, tonight, while it still can. So let the last picture be a simple one. Somewhere out there, unimaginably far, a galaxy poured its light into the dark long ago. That light travelled for billions of years across space that would not stop growing beneath it, stretching, reddening, thinning as it came, and tonight a small part of it finally arrives, brushing against the Earth, brushing against you. By the time it lands, the galaxy that made it has long since drifted beyond any reach. It may already have slid past the edge, gone from any sky that could ever answer it. You are looking at something that is, in every way that matters, already gone. A portrait of a place that no longer keeps in touch with here. That is what Redshift has been telling us all along. Not a warning, not a threat. Just the quiet, patient fact of a universe too generous to hold still. It grew, and it is growing, and the light still finds its way to your eyes across all of it. You do not have to hold any of these numbers. You do not have to remember the names or the distances. Let them settle where they land. The light will keep arriving whether you follow it or not, faithful and unhurried, from a cosmos that has already moved on. Breathe slowly. Let the sky do what it does without you. Somewhere the space between two galaxies is widening by a fraction you will never feel, and it changes nothing about the warmth of the room around you or the weight of you against the bed. The rush is real, and it is vast, and it is also the gentlest thing there is, spreading out so patient it takes 100 billion years to finish a single thought. You're here for the good part, the lit part, the part where the sky still remembers where it came from. Let your eyes close on that. Old light landing softly, a universe leaning away in every direction, quietly, kindly, with no hurry at all. There is nothing here you need to chase and nothing here you need to hold. The colour in the starlight will keep telling its story long after you have drifted off, and it will still be there, faithful when you wake. Rest now. Let the distances go. Let the reddened light of 1,000 vanished galaxies fall over you like the softest possible blanket, and let it carry you down into sleep. Sleep well tonight. Good night.